In this video, we'll look at graphing rational functions. So we've learned a lot about asymptotes, both vertical, horizontal, slant, and even parabolic asymptotes, maybe a couple of those. We've looked at holes and what happens around holes. We looked at end behavior. Of course, we know how to find x and y intercepts. So in this video, we'll kind of consolidate all of that learning into a process for quickly getting all the information that we need to graph any given rational function. So we'll review really quick all the things that we've learned up to this point, and then we'll graph one. So of course, the definition of vertical and horizontal asymptotes. Vertical asymptotes are defined by a line x equals a, whatever a is. Of course, we can talk about the behavior as the rational function approaches any given vertical asymptote from either the left negative side or the right positive side. And similarly, the line y equals b for whatever b is a horizontal asymptote, and we can talk about behavior as x approaches positive or negative infinity as it goes towards a particular y value. To find asymptotes, we need to compare the degree of the polynomial in the numerator to the degree of the polynomial in the denominator. If n is less than m, then we have a horizontal asymptote at the line y equals 0. If n is equal to m, then we just look at the leading coefficients and put the leading coefficient of the polynomial in the numerator over the leading coefficient of the polynomial in the denominator. And then, of course, if the degree of the denominator is greater than the degree of the polynomial in the numerator, then we have no horizontal asymptote, but instead we have a slant or maybe even a parabolic asymptote. And the vertical asymptotes are just all the lines x equal a, where a is 0 of the denominator. For holes in rational functions, if we have a factor that both the numerator and the denominator share, we can cancel that factor, but we also have to remove that value of x. So if we had a factor x minus 2 in both the numerator and the denominator of some rational function, we could cancel that factor no problem, but then we have to put a hole at x equals 2. And to find the y value of that hole, so we can get the coordinate pair, we just plug it into r of x, our original rational function, with that factor canceled. And then slant asymptotes, like I said, if the degree of the polynomial in the numerator is greater than the degree of the polynomial in the denominator, then we can just use the division algorithm. We'll typically end up with something that looks like r of x equal ax plus b plus the remainder over the quotient. Okay, so with all that in mind, the process to graph a rational function. First, we'll factor both the numerator and the denominator. We'll find the x and y intercepts. We'll find any vertical asymptotes and look at the behavior around vertical asymptotes. We'll find any horizontal or slant asymptotes, implicitly maybe parabolic or cubic asymptotes, as it might happen, and then look at the behavior around those. Then we'll grab a couple test values between vertical asymptotes, and we will graph the rational function. So this process, 6 steps, hopefully helps you consolidate all the different steps to graphing a rational function. So now, with all that in mind, let's follow this process and graph a rational function. So we will graph r of x equals x cubed minus 2x squared plus 3 over x minus 2. So the first step is to factor both the numerator and the denominator. Of course, the denominator is already factored because it's a polynomial of degree 1, so we need to look at the numerator and factor that. Just to try to minimize the overall length of this video, I'm not going to go through the whole process, but suffice to say that you could use the rational roots theorem, you could use Descartes' rule of signs, you could use the remainder theorem, you could use any combination of the theorems that we learned in the sections prior to this section to help you factor. When I look at the numerator, I notice that -1 looks like it might work, so let me just try that to confirm. This is the remainder theorem, remember? So we try p of -1, and that gives us -1 cubed minus 2 times -1 squared plus 3, and that does happen to equal 0. So then we do synthetic division. We're trying -1 into 1, -2, 0, and 3. Drop 1 down, -1 times 1 is -1. -2 plus -1 is -3. -1 times -3 is 3. 0 plus 3 is 3. -1 times 3 is -3. So we have 0. That is indeed a factor. So we can factor our rational function r of x into x plus 1, x squared minus 3x plus 3 all over x minus 2. So I'll remove all this now. We'll do the next step. So I'll just delete that and move our factored form up. All right, so now we need to find the x-intercepts. To find the x-intercepts, we set the numerator equal to 0. So we have x plus 1, x squared minus 3x plus 3 equals 0. So obviously, one of our zeros will be at x equals -1. So what about x squared minus 3x plus 3 equals 0? I don't see an obvious way to factor that, which makes me think that we should use the quadratic formula. So we'll have -b plus or minus square root b squared, which would be 9, minus 4 times a times c all over 2 times a. Now, I see a problem here because in the radical, we're going to have 9 minus 12, which would be -3. So that implies no real. So we're only going to have x-intercept at x equals -1. So our singular x-intercept is -1, 0. But y-intercepts. So now we plug in 0 into our rational function. So we get 0 cubed minus 2 times 0 squared plus 3 over 0 minus 2. So that's -3/2, which then tells us that the coordinates of our y-intercept are 0, -3/2. So vertical asymptote now. So the vertical asymptote, we only have 1 0 in the denominator. So our vertical asymptote will be at x equals 2. For the behavior near the vertical asymptote, let's look at as x approaches 2 from the negative side and as x approaches 2 from the positive side. So you can do these test values, but as we approach 2 from the negative side, from the left-hand side, our y value will go to -infinity. And then as we approach 2 from the positive side, our y value will go to positive infinity. Okay, so now for the horizontal asymptote. If we look at the degree of the polynomial in the numerator, we can easily see that it's greater than the degree of the polynomial in the denominator. So that tells us that there's no horizontal asymptote, but instead some kind of slant parabolic cubic asymptote. So now we need to divide x minus 2 into x cubed minus 2x squared plus 0x plus 3. Can't forget about the placeholder ones. Plus 0x kind of helps us keep track of each of the terms. So what do we need to multiply x by to get x cubed? We need to multiply it by x squared. So then we have x cubed minus 2x squared. We subtract that, so we have 0, and we have plus 0x. So that, nothing happens. So we pull down the next one, 3, and obviously we can't put anything. X minus 2 can't go into 3. So we can rewrite our rational function as x squared plus 3 over x minus 2. So this tells us that our asymptote, I'll just write asymp, is the line, is the parabola y equals x squared. Okay, and I think that's all the information that we need. So let's start putting all of this onto our graph. So we have x-intercept at -1, 0. We have a y-intercept at 0, -3/2. We have a vertical asymptote at x equals 2. right here. We have another asymptote along the parabola y equals x squared. So we know that that would look something like this. And then to try some test values, if we do 1 minus 2 plus 3 over negative 1. So 1 minus 2 would be negative 1, plus 3 would be 2 over negative 1, so we get negative 2. Plug that in. And then now maybe we can kind of get a sense, but let's test R of 3 as well. That gives us 27 minus 2 times 9, which would be 18 plus 3 over 1. 27 minus 18 would be 9 plus 3 would be 12 over 1 is 12. So then at x equals 3, we should be way up there. Okay, now I think this is enough information to plot. So again, we kind of draw into our asymptotes, something like this. And then we have to flip back over. And so we come down from the top way up here and kind of trace along our parabola. So kind of an interesting rational function in this case. But that's the process. So you start with factoring the numerator and the denominator, find your x and y intercepts, find vertical asymptotes, look at the behavior as you approach that asymptote from both sides, find the horizontal or slant or parabolic asymptotes, find a couple of test values between vertical asymptotes, and then pull it all together on your graph paper.